Now we are diving in the world of stable diffusion checkpoints, models, and low rank adaptation, known as LoRa. Whether you are an AI enthusiast, a machine learning practitioner, or just curious about the technology, this video will help you understand these concepts and how they're shaping the AI. So let's get started. First, let's talk about stable diffusion checkpoints. To understand this, we need to briefly cover what diffusion models are. So diffusion models we covered in the previous video, but let's have a recap. These are a type of generative models that creates new data samples by iteratively refining noise until it forms a coherent output. This process is akin to developing a photograph from a film negative, where the image gradually becomes clearer over time. So stable diffusion checkpoints are specific safe states of these models during the training process. These checkpoints are crucial because they allow us to resume training from a specific point, ensuring that we don't have to start from scratch if we encounter issues. They also help in fine-tuning models for specific tasks without retraining the entire model. For example, imagine you are training a model to generate high-quality images of landscape. You have been training for days and now you have saved several checkpoints. If your training is interrupted or you want to tweak the model to better generate specific types of landscapes, you can simply load a stable diffusion checkpoint and continue from there. Now that we understand these checkpoints, let's move on to model themselves. In the context of stable diffusion, models refer to the underlying architectures and algorithms used to perform the diffusion process. These models are trained on vast datasets to learn the complex patterns and structures within the data. There are various types of models used in stable diffusion, each with its unique characteristics and applications. Some popular models include denoising diffusion, probabilistic models, known as DDMPS, and score-based generative models. For example, consider a model trained to generate realistic human faces. This model has been trained on millions of images of faces, learning the intricate details that makes each face unique. When using stable diffusion, the model starts with random noise and gradually refines it, using its learned knowledge to generate a high-quality image of a human face. Next, let's explore LoRa, or low-rank adaptation, and its significance in stable diffusion models. LoRa is a technique used to adapt large-scale pre-trained models to new tasks with minimal computational resources. It leverages the idea that most of the information in these models can be represented using a low-rank approximation, significantly reducing the complexity of the adaptation process. This is especially important in stable diffusion models, where adapting a pre-trained model to a new task or dataset can be computationally expensive and time-consuming. Suppose you have a stable diffusion model trained on generating images of animals and you want to adapt it to generate images of cars. Using LoRa, you can efficiently fine-tune the model to new tasks without having to retrain it from scratch. This not only saves time but also computational resources. Now, let's see how LoRa works in practice with stable diffusion models. LoRa operates by identifying the most critical components of the model's parameters that need to be adjusted for the new task. It then creates a low-rank representation of these parameters, significantly reducing the number of parameters that needs to be fine-tuned. This approach ensures that the model retrains most of its pre-trained knowledge while efficiently adapting to the new task. Example: imagine a stable diffusion model trained on generating images of nature. By using LoRa, you can adapt this model to generate images of urban landscapes. LoRa will focus on adjusting the specific parameters related to the new task, such as recognizing buildings and streets. while preserving the model's understanding of general image structures. Let's discuss the benefits and applications of using LoRa in Stable Diffusion models. The primary benefit of LoRa is its efficiency. By reducing the computational resources required for adaptation, it makes it feasible to fine-tune large-scale models on specific tasks, even with limited hardware. LoRa also enables faster experimentation and iteration, allowing researchers and developers to quickly test and refine their models from different applications. Some applications of LoRa in Stable Diffusion includes image generation, video synthesis, and even natural language processes. For instance, in the entertainment industry, LoRa can be used to adopt models for generating special effects in movies or creating realistic animations. Finally, let's look at the future of Stable Diffusion and LoRa. The future of Stable Diffusion and LoRa is promising. As these technologies continue to evolve, we can expect even more efficient and powerful models capable of generating high-quality data across various domains. So the integration of LoRa with Stable Diffusion models will likely lead to breakthroughs in areas such as personalized content creation, automated design, and advanced simulations. For example, imagine a future where designers can use Stable Diffusion models with LoRa to quickly generate custom designs for products, or where filmmakers can create entire scenes with minimal input, relying on AI to fill in the details. In conclusion, Stable Diffusion checkpoints, models, and LoRa are revolutionizing the way we approach generative AI. By understanding these concepts, we can harness their power to create more efficient and adaptable AI systems.